Okay. The scalar product, before I do begin, if you check in Moodle, you will see that there is Dr. Khan. There is a webinar series. It's not YouTube, but it's a public domain academy thing, and it does go into the basics of scalar and matrix arithmetic very, very thoroughly. And if you are wanting to get the finer points, that's absolutely fine. I do suggest you go in there just to actually tweak things. Today's session may well be enough for you, but if you want something a little bit more detailed, it's fine. He does it in a series of tutorials of sort of 7 minutes, 8 minutes, 10 minutes, and so on. And it does actually refer to things like the cosine rule and what that's all about. So it does actually assist as far as that's concerned. Okay. The scalar product of two vectors, and we have two vectors which can be in two-dimensional space, three-dimensional space, or of course n-dimensional space, are constructed by taking the component of one vector in the direction of the other and multiplying the magnitude of the other vector. And essentially we can perform these operations either algebraically or geometrically. And for example, to give an example, you'll see it on the next slide as well, work is done when an object is displaced by a force. The work done by the constant force is defined as the product of the magnitude of displacement times the component of force parallel to the said displacement. And that is actually shown as an example here. So we have here, the force is, unfortunately the terms are not the same, but we have this one here times this one here and the angle between the two. If one actually then equates these two being multiplied together, we take the cosine of the angle between them. Now this is what I'm referring to with Dr. Khan. He does actually give you some examples there because this does relate to the cosine rule, and he gives you the full derivation of that. And remember the cosine rule and sine rule and such like, which we probably will investigate further along because we're going to need them anyway, but they are in relation to any triangle, not just a right angle triangle. So all I'm trying to do there is show you some sort of applicable example in relation to the dot products associated with vectors. Algebraically, please guys do stop me if there's any comments or anything like that. It's absolutely fine. Algebraically, it is the sum of the products of the corresponding entries of the two sequences of numbers. So if you have the dot product of two vectors, a1, a2, dot, dot, dot to an, and b is equal to b1, b2, dot, 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 bn. Now this is of course showing it in the common or generic form of an n-dimensional space. And if we were looking at a1, a2, it would be a two-dimensional environment. a1, a2, a3 would be a Euclidean three-space, 3D geometry. So the dot product is a dot b, which is equal to the summation from I equals 1 through n of ai bi. So it's all the valid numbers of I running from a1 b1 plus a2 b2 dot 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 through to an bn. Okay. I'm sure everyone is fairly happy with that. I hope you are. But please do stop me. Has anyone had a chance to actually look at the materials in Moodle? Maybe an unfair question. And the other thing is there was the tutorial slide pack which was put up, but it was put up fairly late, I do know. And that's my fault, incidentally, not... Okay, that's fine. Okay, good for you, Sam. That's absolutely perfect. All right. So in three-dimensional space, we want to find the dot product of the vectors as follows. Can anyone tell me where we would start with that? Just writing it down. It's going to be 1 times something plus 3 times something times from minus 5 times something. 1 times, let's just go ahead. 1 times what? Sam, you're going ahead there. Fantastic. 3 times plus 3 times. Yep, that's correct, Isaac. Plus 3 times what? 3 times minus 2 plus minus 5 times minus 1. And this is shown on the next slide. Here we have it. 1 times 4, 3 times minus 2, minus 5 times minus 1, which gives you 4 minus 6 plus 5 equals 3. Everyone happy with that? Thanks, Isaac. Thanks, Sam. Sorry, I missed it as I flipped the slide over. And my apologies, by the way. Sometimes the slides sort of flip over and you know, you're typing away, and we have this disconnect in terms of timing, and there's nothing intentional with that. And by the way, also, I did mention it to the other group, the mathematics shown here is just an introduction in here. Some of it may be basic for some of you, and some of you may have forgotten some of this, some of you may not have seen some of this, it's just, or you need to revisit it. Whatever the situation with all of you, please do accept I am not trying to be condescending in any way, but I have to kind of go in and assume that I need to explain it all. So please just bear that in mind. And if you are finding it easy, well, that's great for you, because then this one lecture you don't need to worry about too much. Okay, so if we talk about the dot product using that was using the algebraic type solution. The geometric definition is the product of the Euclidean magnitudes of the two vectors, and this double vertical line refers to the magnitude of the vectors. Okay, the distance from here to here in terms of A, obviously it's not with a, you know, it's a straight line, and the cosine of the angle between them, and this is actually derived from the cosine rule. So we have here A dot B is equal to magnitude of A times magnitude of B times the cosine of the angle between the two. So the properties associated with the dot products, A dot B is equal to B dot A, and you can use a fairly loose proof as far as I'm concerned, where we have A dot A is equal to the magnitude of A times the magnitude of B times the cosine of theta. And these are just real numbers. You can change B and A around, the magnitudes and cosine of theta, which is equal to B dot A. I say it's a loose proof. It is perfectly true. The distributive over vector addition, A dot B plus C, is equal to A dot B plus A dot C. Now the reason why these are all being stated is that it is by and large like normal multiplication, but it is not always like that, so you have to be careful. Bilinear, where you have a factor in here, A dotted with RB plus C is equal to R is just a constant being pulled out, times A dot B, so let's rearrange, plus A dot C. And scalar multiplication, which frankly I think it kind of covers is the bilinear and scalar cover one another. C1A dot C2B is equal to the two constants multiplied together times the dot product of the two vectors A dot B. Anyone know what an orthogonal situation is? What does orthogonal mean? Okay, basically, when we talk about orthogonal, that means they are perpendicular to one another. And essentially, two non-zero vectors A and B are orthogonal if and only if A dot B equals 0. Can you tell me why they would be 0? Just by looking at the geometric type solution of a dot product. If they're orthogonal, the degree between them is, what's the degrees between the two vectors? If they are orthogonal, I've told you it's perpendicular. What is the angle between the two of them? It's going to be 1, 2, 3. Thank you, Sam. Ah, good, I can rely on Sam. 90 degrees. Right, I've explained that to you. It's 90 degrees. And what is the cosine of 90 degrees? It's 0. So therefore, cosine of 90 degrees is 0, so the dot product is 0. Okay? Good, good. Right, we're now going to carry on. We're going to do an actual example both ways here. And this is a 3, 4, 5 triangle, where, I don't know, just that was the way I was brought up. 3, 4, 5 triangle is an isosceles, not an isosceles, right angle triangle, where it's a factor of 3, obviously. 2 times 3, 2 times 4, 2 times 5, and then a 5, 12, 13 triangle. And basically, 6 squared plus 8 squared will equal 10 squared. And similarly, 5 squared plus 12 squared is equal to 13 squared. So you can get the length then of B, the length of B, you can actually work it out from the other two sides by means of what plus what? Anybody? No, I'm just be doing a very basic thing at this stage, Sam. Just an algebraic expression in terms of the sum of the square of the two sides is equal to the sum of the hypotenuse. If we look at this on the left-hand side here, basically 6 squared plus 8 squared. If you add those two together and take the square root of it, what do you get? 6 squared is 36, 8 squared is 64. Add the two together, it's 100. Take the square root of that, it is 10, precisely. And that is the length of the vector A, by taking the sum of the squares of the two sides and actually adding them together and then taking the square root. That's all I was referring to as a basic geometrical type rule. Okay, but what we're trying to do here is not that, that was an aside. We're trying to calculate the dot product of the vectors A and B. I would ask you to jot these down, please, and basically we can then look at, I'm going to do the second one first, A dot B, which is just the two components, minus 6 times minus 5, minus 6, remember this is in a negative direction, times 5, did I say minus 5? I shouldn't have. Minus 6 times 5, plus 8 times 12, the two y components. 8 times 12. Okay, adding them together, you get 66. Or you can do it the other way around by using the length of the vectors. Okay, the length of the vectors, and the length of vector A is 10, and the length of vector B is 13. So we have here 10 times 13 times the cosine of the angle between them, which comes out to be 65.98 or 66 rounded. And that's just trying to illustrate the solution there. Guys, is that all right? I need to get some sort of feedback. Sam's the only one giving me feedback. There's a little bit here and again from Isaac and one or two others. But if you're following, that's grand. But if you're not following, I do need to know. Good, good. Okay. All right. Calculate the dot product for the following two vectors. Okay, Mark, fair enough. I'm just trying to get a little bit of participation in the room here. But please, you know, you surely have a bit of paper handy, don't you? Okay. Fair enough. All right, I'm not trying to get on anyone's case, guys. I'm just trying to get it through and trying to make sure that everyone understands. That's my objective, so please don't take it personally. Right, calculate the dot product for this. Now I'm going to give you a hint. You don't even need to look at the numbers. Cheers, Mark. You don't even need to look at the numbers. Remember, the dot product is the length of the two vectors times the cosine of the angle between them. What's the dot product of these two? Exactly, Isaac. Bingo. Thank you very much indeed. Because, of course, it is a right angle. Yeah. They are orthogonal to one another. And it is proven both ways. They don't even bother to put the numbers in here for A and B, the lengths. They don't need to because the cosine of 90 degrees is, of course, 0. Here they do it the long way around algebraically, which is fair enough. I don't have any issue with that. Minus 12 times 12 plus 16 times 9 minus 144 plus 144 is 0. And just looking at the dimensions again, 12 and 12 and 9 and 16. Okay. Now, of course, the answers, the questions are chosen deliberately there, but nevertheless. Right, now, to do an application of this, Sam has measured, not you, Sam. This hasn't been changed for Sam van der Merwe, but there we go. Sam has measured the endpoints of two poles and wants to know the angles between them. So here we are in 3D. Okay, so we're in 3D. We've got our x-axis, we have our y-axis, and we have our z-axis. And we have the couple points, the 3 points, 927 and 480. I would just ask you quickly to write those down. Sorry, the 480 is A and the 927 is B. Just write those down quickly. And we're just going to run that through how that actually works. Okay. Thank you. Now, we have 3 dimensions, so you're just reminded here not to forget the z component. But the dot product is A times B going through the x, the y, the z. So we use 9 times 4 plus 2 times 8 plus 7 times 10, which gives us 122. All right? So that is the dot product. We can also work out the length of the vector A, which is just, and this is why I was doing it earlier on, we square each of the components, the x components, the y components, and the z components, x, y, and z. Remember, I did it for you just earlier because the two sides of a right-angled triangle in a two-dimensional environment would just have the x and the y, but you add the squares of them together and you take the square root. Now, of course, we've got the z component to contend with as well, and it works out to be the root of 180. Is everybody happy with that? The length of vector A is root 180. Square root. Fantastic, guys. Thank you. Okay, fantastic. Right, so now we've got the length of vector A. We do the same for B. We just square each of the components within, they are just particular to each of the vectors. It's nothing to do with one another. And basically we square them, add them together and take the root. These ones are just root 134. Now, the equation which we have is A dot B is equal to the length of A times the length of B times the cosine of the angle between them. That is the fellow we are trying to find, the angle. So now shove everything in there. We've calculated everything. We've calculated the dot product up here. It's 122. We've got length of A and length of B is root 180 times root 134 times the cosine of theta. We now make the cosine of theta the subject of this equation. So cosine of theta is equal to 122 divided by root 180 times root 134, which works out to be 0.7855. Lads, I'm not going to do this on a calculator. That's absolute waste of time. You can check this later if you so wish. But essentially, theta is then the arc cosine, or the arc cosine of 0.7855. It's the angle whose cosine is 0.7855, which is equal to 38.2 degrees. So if you get the idea here, we've actually used both definitions in order to calculate the angle. That is quite important, everybody. Okay, fantastic. You sure you don't want to drink, Mark? A shot of brandy shoved in there. I'm glad to hear that, Sam. I'm glad to hear that. Okay, just a couple of things here. I didn't know where you were, Mark. I thought you were more or less in my time zone. But clearly you're not. Where are you? You must be in the Americas somewhere. Okay. When I say Americas, I meant USA/Canada. I didn't know which. Brilliant. Okay, good stuff. I'm going there next month. No, I'm not, in January. Whereabouts are you, Mark? Ah, lovely. I was in Philadelphia in May. Really like Philadelphia. Okay. Actually, I was a little bit south of that, but I went to Philadelphia for a couple of days. Yeah, I was down south. I can't remember the name of the place now. About 30 miles south. Okay, basic joints. This is just giving you some sort of indication, and this is just introducing terminology into the room, that's all. But we talk about a revolute joint, which has 1 degree of freedom, which the variable here is y, and essentially, you've got your y1, y2, and y0. These are your excuse me, I'm getting tongue-tied here. These are referred to as your degrees of freedom. But a revolute joint, which is also known as a pin joint or a hinge joint, there you actually have successive ones in this diagram, is a 1 degree of freedom kinematic pair used in mechanisms. You've got a single axis rotation, and it's used in places like a door hinge, folding mechanisms, stuff like that. So they do not allow translation or sliding linear motions. And yeah, so it's hinge joints basically. The other two are a prismatic joint, which is a linear, and they're using different variables here, and that's one thing about this game. The naming does vary, unfortunately, but we're using the names which have come up from different people because you do need to be aware of it. So they're not using X here necessarily, they're using D. So this is also 1 degree linear. It's a sliding mechanism going through. And then the third one is a spherical joint, which has 3 degrees of freedom. And this has your variables y1, y2, y3. That's the way they have phrased it. And again, it's not necessarily my choice that I would like, but whoever has written or done this diagram has used that in their terminology, and it's good to be aware of the different terminologies involved here, guys, please. All right, so a spherical joint is the most complicated. It's a ball joint in effect, and you'd find these in automobiles. and they are bearings which connect control arms to steering knuckles, as an example. You would find them in a ball and socket type joint within the human being, one of course being the hip or the shoulder, and such like. Okay, so the mass review here, the dot product of two vectors, is just the lengths of the two vectors times the cosine of the angle between them. And this is based upon the cosine rule, which is a basic trigonometrical function. If you don't remember it, Dr. Khan's videos, or Google it. Okay? And the matrix representation, doing it from a geometric perspective, you have all the components, AX and AY, and there may be AZ as well in here, times, or should I say dotted with BX, BY, it's just AX, BX plus AY, BY. It's using the constituent component.